All right, ladies and gentlemen, welcome back to another video with Mr. Kenton for HL Chemistry. And this is covering the very last section of Topic 3 and Topic 13, which is looking at periodic trends. And we've also been taking a dive more deeply into understanding some of the things about transition metals. And the last thing we're going to be taking a look at today has to deal with colored complexes. And so looking at why do the ions of the transition metals make or produce such colorful solutions, talking about it from that perspective. And so we're going to be diving into and looking at the atomic structure, looking at how the d-orbitals are changing and things like that as we look at these colored complexes. So I think this is going to be a pretty neat topic. Again, it's not something that we have looked at previously, so this should be new for everybody. So this should be pretty fun stuff. So hopefully you guys are excited. Let's go ahead and dive in. Now, here again are the pretty much the kind of teaching things that we're going to be going through. I don't want to read this slide to you, ladies and gentlemen. It's way too much text. But please make sure that you understand, you look at this. This is what we're going to be analyzing with this particular topic, and here are some things that we should consider as we're moving forward, okay? Right? And then it's going to be broken down into some more understandings and key ideas. I'm just going to go through these pretty quickly so we can get into kind of the new stuff. So one thing we need to understand, the D sublevel, we know it's got those 5 orbitals. What's going to happen? They're going to split into 2 sets of orbitals of different energy in a complex ion. So instead of them being degenerate in nature, you're going to have d orbitals that have different energies within complex ions. And that's, we got to be clear here. This is specifically for complex ions. We also need to know that complexes of d-block elements are colored. And so as light is absorbed, what happens, an electron gets excited between those split d orbitals, the low energy and the high energy, and so it causes those electrons to move there. We should understand that the color that's being absorbed is going to be complementary to the color that is observed, okay? And we should be able to explain the effect of the identity of the metal ion, the oxidation number of the metal, and the identity of the ligand on the color of the transition metal ion complexes. We should also be able to explain the effect of different ligands on the splitting of the d orbitals in transition metal complexes and the color observed using the spectrochemical series, which can be found in the IB chemistry data booklet. All right, here we go. So this is a table and it gives us colors of specific transition ions, right? And I think it's interesting that scandium 3+, scandium 3 ion, and zinc ion are the only ones that are colorless. And then you've got everything else that have their characteristic colors, right? Now, the goal is not necessarily for you guys to memorize all those colors, but I want you to consider the reason for scandium 3+ and zinc 2+ being colorless is because they don't have any d-electrons that can move within the d orbitals. Okay, that's why they're colorless. All right, so how do we determine, or what's going to determine the color of a complex ion? Well, it's going to depend on 4 factors. The first being the nuclear charge and density of the central ion. So, you know, we think of nuclear charge, we're thinking of how many protons does it have? And what about the charge density around that central ion? You know, you've got the charge density of the ligand. How many charges are surrounding the ligand specifically? Third thing we want to consider here, the number of d-electrons present, and hence the oxidation number of the central ion. And then lastly, the shape of the complex ion, right? Different arrangements are going to allow for different colors to be observed. Now, when we're looking at the color of the complex ion, we need to consider and remember that this is not the same thing as when we do like the flame test, for example, right? In the flame test, we're literally causing electrons to move closer or farther from the nucleus, meaning they could go from, let's say, the 4th energy level to the 3rd energy level, or going from close to the nucleus to far away from the nucleus. But in solution, it's very different. What we see happening is that the transition metals, what they're doing is they're absorbing light. And as we talked about earlier, what we see happening is that the d orbitals actually split. Instead of being degenerate, they split into two separate sublevels. So you've got like we'll say like a d1, 1, 2, and 3, and then a d4 and 5. The 4 and 5 are going to be higher energy than 1, 2, and 3, right? And so that's what's going to be taking place when we talk about colored complexes in solution. It's not going to be the same thing as when electrons were being excited or returning to their ground state in the flame test lab. Okay. Now, we're familiar with the electromagnetic spectrum. We understand that visible light is in the ranges of 400 to 700 nanometers. And we know that the color that we see from the visible spectrum is going to depend upon the wavelength of the light. And so there we've got a good range of values that correspond to our visible spectrum, right? We notice we've got our red, orange, yellow, green, blue, and violet. And, excuse me. And what we're seeing is as we move from red to violet light, we see a decrease in that wavelength, which means we should be seeing an increase in the energy of the light as we go from red to violet. Okay. Now, the color of a substance is going to be determined by which color of light it absorbs. Okay. And so certain ions, they absorb certain colors of light. And then when they transmit light, they're going to transmit light that is complementary to the light that they absorbed. So we look at it from this perspective. This iron 3+ ligand complex ion, which has these waters attached to it, appears orange because it absorbs blue light. So that complex, it absorbs blue light, and then when it transmits out orange light. And what we see is that orange is the complementary color of blue, right? And you can take a look at the data booklet in the on Google Classroom. The color wheel can be found there. That's how you can identify your complementary colors as it pertains to the colors of light that are absorbed and then what's being transmitted, right? Now, let's talk more a little bit about what's going on with these d orbitals. So we know that in a transition metal, if it's not an ion, we know that the d orbitals in a transition metal, they all have the same energy and are said to be degenerate. That's what we've always communicated to you guys about orbitals, is that they would always be degenerate. They have the same energy. Well, when you have a ligand and it approaches a transition element, what's going to happen are the lone pairs of electrons on the ligand, right, are going to cause the d orbitals of the transition element to split into two sublevels. So you're going to have one section that's going to contain some d-electrons, and you have another section that's going to contain some d-electrons. So you're going to have a splitting of that d orbital. And the reason for that has to do with the ligand that's approaching the transition metal. So we think about in the previous slide, we had iron in the water molecules, the lone pairs are approaching that ion, and it's going to cause the d orbitals to split into two separate sublevels, right? They're still d sublevels, so they're still d orbitals, but the d orbitals that have been split are going to have differing energies. Now, when light passes through the solution, what's going to happen is that the electrons that are in that lower section, right, can be excited and be moved into kind of those higher orbitals within that d sublevel. And when that happens, that's when we see that transmission of light within our solution. Now, an amount of energy is going to be absorbed, and that's going to depend upon the frequency of the light, right? We understand that different lights give off different energies, therefore, different amount of energy is going to be transferred into the solution. Now, if a photon of green light is absorbed, then what we would anticipate is that the complementary color of red light is what would be transmitted if that photon of green light is able to kick up an electron within that particular substance. Now, when you start to look at, well, how do we determine the energy separation between those d orbitals? Well, that energy separation is going to depend on a couple of factors, right? First thing we need to consider is the nuclear charge and identity of the central metal ion, right? So how many protons are in the nucleus of our metal ion? That's going to determine part of that energy separation. Second thing, the charge density of the ligand. You know, how much charge is situated around our ligand that's approaching our metal ion. The shape of the complex ion is going to determine a lot of that energy separation between the d orbitals. And then the number of d-electrons present within your transition metal, and thus the oxidation number of the central ion, are going to be key in determining the energy separation between those d orbitals. All right, so let's dive into and look at specifically how does nuclear charge and the identity of the central metal ion influence the energy separation and the color of our complex. So what we know is that ligands tend to interact more effectively with the d orbitals of ions with a higher nuclear charge. Right, and that makes sense because you get stronger interactions when you have greater charge differences. And so since the lone pairs on the ligand are what are trying to interact with our metal ion, if you have something that has a greater positive nuclear charge, then it's going to bond and bind more effectively with that metal. Now, if we think about it, we looked at the number of coordinate bonds that can be formed within a complex ion. So the coordinate bond is going to be stronger with ions that have a higher charge, right? So a +2 versus a +3, right? The one with a +3 would have a stronger coordinate bond. Likewise, as we increase the charge, the more they can absorb light in the higher energy portion of the visible light spectrum. So what we would anticipate, I'm just using this as an example, something that has a 2+ charge, maybe it can only absorb light that's in the yellow or the green portion of the spectrum. But something that's got a +3 charge or a 3+ charge, maybe it can absorb light that's in the blue or maybe even the violet portion of the electromagnetic spectrum. Right, and so here's some specific examples, right? So the manganese 2+ ion, it absorbs light in the green region, which is approximately 490 nanometers, while iron 3+, it absorbs light in the blue region, which is approximately 450 nanometers. And so as we can see there, the charge impacts the energy that can be absorbed by the ion. And just as a quick reminder, I know we've looked at this previously, but remember that the shorter the wavelength, the higher the frequency it will be, and the higher the amount of energy that will be given off as a result of that absorption. Okay. All right, let's take a look at how the charge density of the ligand is going to impact our colored complexes. So we looked at how the nuclear charge and the charge on the ion itself can impact that distance between the d orbitals. Well, the energy separation of the d orbitals depends also upon the charge density of the ligand as well. And so the lowest charge density is going to repel the d electrons the least. So that means you're going to have a smaller gap between your split d sublevels. And so what that means is that it's going to absorb longer wavelengths, therefore it's going to absorb lower energy in order to cause those transitions to take place. Now, our highest charge density ligands, they're going to repel the d orbitals the most. So what that's going to do is it's going to create the greatest separation between your two different sets of d orbitals, and therefore it's going to absorb shorter wavelengths of light, which means you're going to be giving off higher, or it's going to take in higher energy amounts. And the spectrochemical series is in section 15 of the data booklet. And essentially what you would do is you would look at those ligands that are listed there, and that would help you determine which ones are going to create the greatest distance between them. And so, like, for example, iodide ion, for example, has the longest wavelength, and so that means it has the lowest charge density, whereas something like carbon monoxide, if you're looking at it, has the greatest or the highest charge density, and so it creates the greatest splitting between the d orbitals, right? And so taking a look at that, it goes from iodide, bromide, sulfide, chloride, water, hydroxide, ammonia, cyanide, and then carbon monoxide, right? So that would be the order. That was from least to greatest. And again, you can find that spectrochemical series in section 15 of the data booklet, so no need to memorize that order. Okay, so we've looked at nuclear charge and the charge of the ion. We've looked at the charge density on our ligand. Now we're looking at the geometry of our complex ion. So the splitting in energy of the d orbitals does depend on the relative orientation of the ligand and the d orbitals within our metal transition metal ion. And we're going to keep it as simple as that. We're not going to talk about specifically which ones are greatest, but it's good to know, or it's important to recognize how that influences that as well, right? And I believe our last point is looking at the number of d-electrons and the oxidation state of the metal ion and how that's going to influence our splitting and the energy of light that can be absorbed and therefore transmitted. Right, so the strength of the interaction between our ligand and the central metal ion depends upon the number of d-electrons, which will then directly correspond to the oxidation state of the metal, right? So again, the interaction is going to be strengthened based on the interaction between the ligand and the central metal ion. That makes sense. And a component that we have to look at is how many d-electrons does that transition metal have? That's essentially what that's communicating to us, right? So we know that iron 3+ has 5 d-electrons and iron 2+ has 6 d-electrons, okay? So how is that going to influence our interactions, right? We know because Fe3+ has a higher charge, we see that it absorbs blue light and it reflects yellow. Now, Fe2+, it absorbs violet light and it reflects green light. Well, we can see there that the Fe2+ is absorbing light that's at a higher energy. And that has to do with the fact that it has more of those d-electrons that are available that are interacting, and so that's why it's able to do that. Now that's different from if we looked at the difference between the manganese 2+ versus the Fe3+, right? So here we're kind of comparing within different ions of the same element, right? So you got Fe3+, the 5 d-electrons, Fe2+ has 6 d-electrons, and so that's where we see that the number of d-electrons does impact the color of light that's absorbed and therefore what gets reflected. All right. And then here's the citations. This all comes from the text. Hopefully you found this insightful. This is also the end. This is the last video that corresponds to this particular topic, which means we're going to be ready to kind of be transitioning out of this section and moving into the next one. So feel free to be asking questions in class. I look forward to seeing you guys again soon, and thank you so much for stopping by. Take care.